Okay, so welcome back to another video. So here we have an infinite sum of -1 to the power n times arctan of 1 divided by f sub 2n. So the capital F represents the, or capital F sub k represents the kth Fibonacci number. And it's also worth noting that the terms we're going to be starting off with is that the sequence we start off with is f of 0 is equal to 0, and then f sub 1 is equal to 1, and then we build up the construction all the way up from these numbers. So yes, we will actually be using the older definition of the sequence of Fibonacci numbers. Nowadays, Fibonacci numbers usually they start with f of 0 is equal to 1, and then f sub 1 is equal to 1, and then it just builds up from there. But here we're going to actually be starting with f of 0 is equal to 0 in this case. So with this infinite sum, from rewriting this, there's actually a bunch of identities we'll be using in relation with Fibonacci numbers. And because there's also with the arctangent, trig function, again, another identity will be used. And it's basically just a form of just rewriting this entire, series over here, and then converting it into a way that it's actually easy for us to evaluate from there. And even with this infinite sum, you're also going to see that we're actually going to be writing things in terms of limits. So that's another thing to, expect. But other than that, let's actually just jump right in. So it's worth noting that the identity specifically for arctan is that arctan is actually an odd function. So we have that arctan of negative a is just some input. For example, it's actually just equal to negative arctan of just the argument a itself. So that's the identity we'll be using. Another identity we will also be using, this is known as Cassini's identity. This is a mathematical identity used for Fibonacci numbers, but that says that for the alternating -1 to the power n is equal to f sub n minus 1 times f sub n plus 1, and then subtract with f sub n square. So you can actually prove this identity by using some matrix theory, specifically with determinants. And I feel it's a more easier way to prove this is simply by induction. So there's and then there's also other proofs that I saw that you can actually use like bijections. Another one is actually a shorter version of using the induction of proving this. So you can go however way you want to show this, but I'm not really going to go into it. And another identity we'll be using, this is for more of Fibonacci's addition law, that says that for capital F sub n plus m is equal to capital F n minus 1 multiplied by capital F sub n plus f sub n, and then multiplied by capital F sub n plus 1. So if you notice that we have a f sub 2n, so simply if I just replace m is equal to n and then just put that back in, so what we have now is that if we plug m is equal to n, so now capital F of 2n is simply just equal to capital F sub n minus 1 multiplied by capital F sub n, add this with capital F sub n, and then multiply this with capital N plus 1. By doing so, now let's actually put in the substitution we need. So let's start off with just the series first, over here, before we can continue forward. So notice that -1 to the power n arctan of 1 divided by capital F sub 2n. Another way I can write this is just positive arctan of -1 to the power n, and then divided by capital F sub 2n. And then from here, we can just replace the, now just go back to, just our original given, so the infinite sum. So let me first just write that again a second time. N is equal 1, then we have -1 to the power n, then arctan of 1 divided by capital F sub 2n. Then all we do is just replace the identity with Cassini's identity over here, and with this, with the inclusion of m is equal to n for f sub 2n, this identity over here. So now we would have the new following identity written as follow. So n is equal 1, then arctan. Then on the numerator, we just replace this with this identity over here, capital F sub n minus 1 multiplied by capital F sub n plus 1. And I'll put a parentheses just to denote like the quantity. So capital F sub n, quantity square. Then the denominator, just plug in this identity over here. So capital F sub n minus 1 times F sub n. Add this with F sub n, and then multiply by capital F sub n plus 1. and then we could just close this off. Now, let's actually do a little bit of rewriting for our input argument. So you'll notice that what I can do is I'm going to divide a capital F sub n multiplied by capital F sub n minus 1 to both the numerator and denominator. So let me first write this argument, the same argument over here. So I said that I'll multiply a capital F sub n, or divide a F sub n times F sub n minus 1 to both the numerator and denominator. So let me write this as a form of like rationals. So multiply F sub n, then F sub n minus 1. Then we just do this under the denominator as well, same thing. And then some terms will cancel each other out. Specifically, if we look at the top, n minus 1 will cancel here, and then the F sub n from over here will cancel. So, and the denominator over here, so this will be just reduced to 1. However, for this piece over here, we're not really gonna eliminate terms from numerator and denominator. We're gonna leave that the way it is, and you'll see why I keep it that way. So now this new argument on the top is capital F sub n plus 1 divided by capital F sub n, subtract with capital F sub n, then divided by F sub n minus 1. All this being divided by 1 plus F sub n plus 1 divided by F sub n, and then this is multiplied by F sub n, and then divided by F sub n subtract 1. So now we just put in this new argument. I think right here is a good space to do it. So now over here we have a new rewritten infinite sum. So n is equal 1, arctan, and then just plug this in. So I'm just going to cut to the next clip. We notice that we actually obtained something with this arctangent function, and I'm going to put a little note that we obtained that this is in a following closed form. So obtain in closed form, and that says that we have the form of arctan of, what is it? Some input a minus b, and then divided by 1 plus a times b. So now, what I'm going to do from here is I'm actually going to prove this little identity of how we get, we can actually rewrite this a little bit even further. So we're going to start off with the fact that if we actually choose two inputs, for example, I'll just call this capital A and capital B. If we start off with the tangent of capital A and then subtract B, we can write this, obviously we know that tan is the way of saying sine over cosine. So sine of A subtract B, then divided by cosine of A subtract B. Now we actually just use the subtraction rule of the inputs. So now the new numerator and denominator can be written as sine of capital A multiplied by cosine of capital B, subtract sine of B multiplied by cosine of A. All this being divided by cosine of capital A, then cosine of capital B. Add this with sine of capital A, and then multiply by sine of capital B. Now from this next step over here, let's see. So now what I'm going to do is I'm actually going to divide cosine of B. Okay, so from here we have our new rewritten form. So this will be sine of capital A, then subtract tangent of B, since that's dividing cosine of B, so sine over cosine, and then multiply by cosine of A. And then over here next is, so divide by cosine of B, so this will be cosine of A on the bottom. Then from here we have sine of A, then multiply by, so sine divided by cosine, so this will be tangent of B. And one more step I'm going to do here is now we're going to divide sine of A, excuse me, not sine of A, cosine of A. And so by doing so, we would have now the top will be tangent of A, then subtract with tangent of B. Then under the denominator, so that will just be 1, and then add this with tangent of A, and then multiply by tangent of B. So we have something of a similar form just like this. Now what we do is suppose if we do some substitution, suppose that if we let the substitution, we let A equals capital or tangent of capital A, and then lowercase b be equal to tangent of capital B. Okay, so now if you just solve for capital A and capital B on its own, then we get that A, or capital A is equal to arctan of A, B, capital B is equal to arctan of lowercase b. then we can see that now over here, let me put it like this. Then from here, we see that this is the equivalent of saying A subtract B. Then that will also have to mean in terms of this is just arctan A and then subtract with arctan of B. So now we have something reduced from here. And so now we can actually rewrite things even a little more further with the infinite sum over here of the Fibonacci numbers. So now let's actually move on to there. So now we have a new infinite sum and we can write that as the following. So the infinite sum n is equal to 1 of, now I'm gonna put this in parentheses, we would have arctan of our first input which would be capital F sub n plus 1 and then divided by F sub n, and add this with, or rather subtract with arctan, and then put in that second input, which will be capital F sub n, and then divided by F sub n subtract 1, and close that off. Let's actually do things, because this is infinite sum, and I mentioned we're gonna do this in terms of a limit, so we can actually evaluate this little partial sum. So now write this as the limit as capital N approaches infinity of our partial sum. The upper index is capital N, lowercase n is equal to 1, of the same thing, so arctan capital F plus 1 divided by F sub n, subtract arctan of F sub n divided by F sub n minus 1. Now, you'll see that if you were to expand this series out, we actually get a little telescoping series. So now what's left is, of course, the first and the last terms of our expansion. Everything in the middle just cancels each other out. So now we have the limit, so the limit as capital N approaches infinity of arctan. So what's left over here, this is the last term, so capital F sub capital N plus 1, and then divided by capital F sub n. Then we subtract this with arctan of F sub 1 divided by F sub 0. We can actually compute some things. So if we notice that we set that capital F sub 0 is 0 and then capital F sub 1 is equal to 1, there's a little bit of a discrepancy and see that we have a 1 over 0 form, which it's undefined. But if we look at this like with the sequence as it increases, we're really just looking things from the right side. So that means we just take the limit as we look at it from 0 from the right side. So really this value is actually going to approach, is going to actually equal to just pi over 2. So we have this. So now we actually have to figure out how to compute this limit over here. So really with just continuity, you actually just compute the limit as, we just now have to compute the limit as capital N approaches infinity of capital F sub n plus 1 divided by F sub n. And assuming that it converges, we'll call this capital L as n approaches infinity. Okay, so what I can do from the numerator is that we can actually replace this with the recurrence relation that this can be written as, so n approaches infinity of capital F of capital N, then add this with capital F, then capital N, subtract 1, and that's divided by this. Then we'll notice that we got some terms that cancel each other out, so we have 1 plus the limit as n approaches infinity, capital F sub n minus 1 divided by capital F sub n, okay? And that's still equal to L. But you'll notice that specifically over here, we can actually, there's another identity we can write this as. So really the limit as capital N approaches infinity of F minus 1 divided by F sub n. This can be rewritten as the same thing as the following over here. So this will be capital F sub n on the top and then n plus 1. And so from there, that means this will actually have to, we set that that's equal to L, so we just replace that and flip it. So in other words, this is actually just going to be 1 over L. And so this is what we have. So 1 plus 1 over L is equal to L. And if you solve this out, so L squared minus L minus 1 equals 0, you'll have, and you just solve that out for, your L's, basically, it's not easy to reduce this, so you just use the quadratic rule. You'll have 2 of the following solutions. You'll have one that's obviously the golden ratio number, so 1 plus the square root of 5 divided by 2. And then another one is 1 minus the square root of 5 divided by 2. So in other words, that's written as negative 1 over 5. But because of the way L is written over here, it has to be greater than 1. So that would have to mean that the 1 minus square root of 5 over 2 excludes, and we're only left with this solution, capital Phi. So therefore we have that L is equal to Phi. And now we're actually just about done. So if we just replace everything back in, so L just goes back into here, that limit's already taken, and we set that this is pi over 2. So therefore our final answer is that this is just equal to arctan of Phi, and then subtract with pi over 2. And so there we have it. We are actually done with this little evaluation over here. And just like that, it is complete. So this was actually a very interesting Fibonacci sum using all these identities. Cassini's identities is actually a really interesting one. But also, I think it was also worth noting as a verification to prove this little trig identity before we can actually, move on and continue with this like new reduced form before we can get to the one we want to achieve. So yeah, that's pretty cool if you ask me.